In Chapter 9, we're finally getting to molecules. We're going to start simple with just diatomic molecules, but of course this is a physical chemistry class, so we really care about molecules and how bonding happens in molecules and how that relates to these quantum mechanical principles that we have discussed up to this point. So, everything that we've talked about up to this point has been, single atoms, and multi-electron atoms, but in chemistry, what makes chemistry is that we care about molecules and reactions and understanding energy of molecules and things like that. So we're going to start with just two atoms. Chapter 10 will get into polyatomic molecules, sort of more normal sorts of molecules that we're used to thinking about in chemistry. But we're going to start more simply with diatomic molecules. And we're going to start with the simplest case we can, simplest molecule we can think of, which is H2. So we'll build up from there. So H2, we have two protons as our two nuclei, two electrons, and our usual approach is that we're going to write down the Hamiltonian for this system, and of course we're going to have to make some approximations from there. In this video, we're going to talk about one of the most important approximations that we make when talking about molecules, which is the Bourne-Oppenheimer approximation. But first, let's consider, how would we write the Hamiltonian for H2? Let's go ahead and kind of map out our system. We're going to have nucleus A and B. We need to give them labels so we can keep track of them. Then we have electron 1 and electron 2. And now we have a lot of interactions going on here. So just going back to our first principles, the Hamiltonian is kinetic energy plus potential energy. And we're going to have kinetic energy. Now we can't really consider our nucleus fixed because there are two of them, right? We can't consider having just our nucleus fixed and everything else moving. So we need to take account all of our particles here. All right, and so we're going to have our kinetic energy terms. We'll have the nuclei moving, so negative h bar squared over 2m, m here being the mass of our nucleus, mass of a proton. And that's going to depend on the del squared operator for nucleus A. And then we'll have another term for nucleus B. That'll look exactly the same. And we have our two electrons as well. Negative h bar squared over 2 mass of an electron, del 1 squared minus h bar squared over 2 mass of an electron, del 2 squared. Okay, so as we can see, as expected, things are starting to get more complicated. Just our kinetic energy term already has 4 parts to it. All right, if we're thinking about potential energy, now we have a lot of interactions to think about. So first we'll have our repulsive interactions. So nucleus A and nucleus B will repel each other. And our two electrons will have a repulsive interaction. But then we also have a bunch of attractive interactions as well. So we have the attraction between electron 1 and nucleus A, electron 2 and nucleus A, and same for nucleus B and electron 1, nucleus B and electron 2. All right, so we have a total of, let's count these. We're going to have a total of 1, 2, 3, 4, 5, 6 different electrostatic interactions, Coulomb potential energies that we need to think about. Let's go and write them out, be specific here. All right, so our potential energy term, we're going to have, and just check my notes over here to make sure I don't forget anything. We're going to have our attractive forces, so negative e squared over 4 pi epsilon naught R1a, R1a representing the distance between electron 1 and nucleus A. Negative e squared over 4 pi epsilon naught R1b minus e squared over 4 pi epsilon naught R2a minus e squared over 4 pi epsilon naught R2b. Okay, so those are all of our attractive forces, and then our repulsive forces are going to be positive. And we don't have it, and we're assuming just H2, so we only have one proton present, so that's where there's no extra charges here, just e squared. And then for our repulsive forces, we'll have e squared over 4 pi epsilon naught RAB, so that's the repulsion between the nuclei, and our sixth and final term, 4 pi epsilon R12. So we have the nuclear repulsion and we have the electron-electron repulsion. All right, so our Hamiltonian is the combination of both of these. So our total Hamiltonian has 10 terms to it, and of course this is not one of our problems that we can solve exactly, so we're going to have to use some approximations first. And so in the next video we'll talk about the Bourne-Oppenheimer approximation, one of the most important approximations made when we consider molecules.